Okay, let's get started. Firstly, let's get some background and context as to what the vehicle dynamics block set does and for whom it answers questions. First of all, automotive OEMs and Tier 1 suppliers must assess vehicles' dynamic performance. And to do this, they have to answer, for example, the following questions. Will the vehicle roll over? What's the stopping distance of a vehicle? And do the stability controls perform adequately? To answer these questions, they typically build prototypes and/or run simulations. The challenges they encounter doing this is that prototypes are quite expensive and you must achieve a good design as early as possible. Specialized vehicle dynamics software is quite expensive and has a steep learning curve. And integrating third-party vehicle dynamics software with Simulink controls is quite cumbersome. We believe that the vehicle dynamics block set can rise to these challenges and help to answer them. Okay, so let's take a deeper look into the vehicle dynamics block set and what it offers. It can model and simulate vehicle dynamics in a virtual 3D environment. You can use the vehicle dynamics block set for ride and handling, as shown in the video below, chassis controls, and for ADAS or assisted driving applications. So what's the features that you get with the vehicle dynamics block set? Well, you get pre-built reference applications, you get a interface with the gaming engine, the Unreal gaming engine, and you get a set of library blocks. Let's take a deeper look into the vehicle dynamics block set examples. So we have a few included examples. The first one is the double lane change, also increasing steer, swept sign steering, a constant radius. Then there's an example of how to use ray tracing and camera placement, and then a kinematics and compliance virtual test laboratory example, and also a stop sign detection within a 3D environment. Let's look at how the game engine co-simulation works between Simulink and the Unreal Engine. So Simulink has the physics of the vehicle, and from Simulink you initialize the gaming engine camera. So Simulink sends to the Unreal Engine the vehicle and the camera location. The Unreal Engine does the rendering, the lighting, the physics of all non-Simulink objects, in other words, the environment, and also handles collision detection. And then being fed back to the Simulink environment is the camera image and the ground height of each wheel. So the height of the ground at each wheel location. Let's take a look at this co-simulation in action. On the left-hand side is the Simulink model, and on the right-hand side was the event being simulated. Let's look at a few use cases for the vehicle dynamics block set. On the screen we see the very familiar V diagram and the approach of model-based design. Let's see where we can fit a few examples. So firstly, let's have a look at a system level design. And within this, we will be taking a look at a complete vehicle model. The complete vehicle model includes a reference generator, a predictive driver, some environmental variables. We'll take a deeper look into the contents of these blocks later on, and various controllers, a complete vehicle model, and the visualization parameters. Utilizing this base model, you are able to customize and add your own inputs and change the model to suit your needs. Some standard driving maneuvers is included in the vehicle dynamics block set. Let's take a look at these ready-to-run pre-built solutions. First of all, we have a constant radius reference application, a double lane change, a swept sign, a slowly increasing steer, also called a J-turn, and a sign with dwell. Let's take a deeper look into the double lane change. Let's have a look at the result of a double lane change simulation done at 80 kilometers per hour or 50 miles per hour. As you can see, the vehicle did not successfully complete the double lane change. Let's have a look in slow motion because there's quite a lot of action. So as you can see, the Unreal Engine is handling the collision detection between the vehicle and these road cones and drums. Let's have a look at where you can find this ISO standard maneuver called the double lane change, how to open it up within the vehicle dynamics block set, and a few settings you can take a look at. The double lane change maneuver is a commonly used test to characterize a vehicle's ride and handling, but it is extremely difficult to get repeatable results from real-world driver testing. Therefore, simulation is ideally suited to this problem, where you can have perfectly repeatable results time after time. Let's switch over to MATLAB and go through the process of opening up this reference app. So what you can do is click on Simulink, open the Examples tab, scroll all the way down to the Vehicle Dynamics block set. In there is a few examples, but we'd like to open up actually the constant radius reference application to show you how you can change after selecting to a different scenario. This opens up a Simulink project. Within this project, we can have a look at the reference generator, and in there we can see all 5 of the examples. Let's choose the double lane change. Then you need to click Set Simulation Time, update the model workspace, and enable the 3D engine, should you wish to. Let's run this demo. This opens up the Unreal Engine in full screen, and as you can see, we also have a bird's eye view plot being rendered at the same time. As it approaches, it turns to go through the cones, and in this case the vehicle has passed the double lane change maneuver. The barrels at the end is just there to show the co-simulation between the Unreal Engine and the collision detection in Unreal and Simulink. Next, let's take a look at the constant radius reference application. This reference application is new in release 2019A. Let's open up the reference generator and have a look at the settings available. Over here you can see you can enable or disable the 3D engine. If you are running these simulations on a computer without the required GPU, you can disable the actual rendering of the scene and have the vehicle dynamics being simulated without the need for this GPU. Now let's take a look at the different scenes available. There is a few scenes included in the vehicle dynamics block set that's been pre-created in the Unreal editor. These are a straight road. This is just a 2-lane straight road, a curved road. So this is a road turning slightly. There is a parking lot, a double lane change scene, as you saw in the previous example, an open surface, which is also known as a black lake, a US city block, a US highway, and also virtual M-City. M-City is a real-world testing facility where vehicles can test autonomous driving features. There's also a large parking lot available. This can be used to test parking valet ADAS features. And lastly, you can also load your own custom scene. This would require to create a scene with the Unreal Editor, and then you can load this also into the simulation environment. You can place your vehicle within the scene, so basically the starting position of the vehicle, using the settings below the cursor. There is a recommended starting position, and this recommended starting position for the scenes have been pre-programmed, but you can also user specify where you want your vehicle to start. Let's take a look at the 5 included maneuvers. We have the double lane change, as stated previously, the increasing steer, a swept sign, a sign with dwell, and a constant radius. We are going to select the constant radius maneuver. We have selected a radius value of 100 meters. Let's change that to 40 meters. And let's change it to kilometers per hour instead of miles per hour. And accordingly also update the simulation time. And you can also select whether you're turning left or right. Let's enable the 3D engine. And let's change the velocity to 60 kilometers per hour. Let's run this simulation and see what the results will be. Here we can see the vehicles. The second vehicle is just included as a reference point. Since we are driving on the Black Lake, there's not a lot of reference points. As you can see, I'm cycling through different views. That's available by pressing 1 to 0 on your keyboard. So there's 10 different views. Okay, I think that shows the reference application and where to find it. Let's have a look at the slowly increasing steer or J-turn. As we can see, the car starts to accelerate until it reaches a set point velocity. At this point, the steering angle starts to increase. We can see the car driving along that increased angle. Over here, we can see the acceleration of the car, and on the bottom we can see the steering wheel angle and the yaw rate of the vehicle. After the maximum steering angle is reached, there is a plateau, and then the steering angle decreases. Here we can see the acceleration response of the vehicle, and on completion we can see the final maneuver. Let's also have a look at the swept sign steering maneuver. In this maneuver we can see a vehicle whose steering wheel is moved from negative 90 degrees to positive 90 degrees at a frequency that's being swept. So in other words, starting out slowly and then faster and faster. Let's have a look at this. So we can see the vehicle reaches a set point speed and then starts to sweep the angle of the steering wheel between these two extremes. Here we can see the acceleration of the vehicle, and over here in blue we can see the steering wheel angle, and the yellow is the corresponding yaw rate of the vehicle. Let's have a more detailed look at the complete vehicle model. Let's open up MATLAB. Let's start out looking at the environment, what's included there. Here we can see we can have wind in 3 different directions and also ground feedback. If you look inside the ground feedback, you can have it constant or being fed from the 3D engine using ray trace to determine the height of the vehicle at the tire positions. And let's go back to the reference application. Next we'll have a look at the controllers. Over here we can see that we have a ECU unit, transmission controller, a brake controller, and a active differential control. Let's have a look at the ECU. This is quite simple. It's a acceleration to torque request that's being, in this case, quite simply done with gain. So the acceleration request is multiplied by the maximum torque of the vehicle. Let's have a look at the rev limiter control. Here we have a one-dimensional lookup table to determine the torque limited rev command. Let's have a look at the transmission controller. Here we have a selection of 3 different controllers that can be chosen using the variant selection. It's a transmission controller having a driver with no clutch controlling the gears, or using paddle gear selection. Here we see the transmission controller, and over here we can see the state flow controller for selecting the gear based on a few inputs. Let's go back to the controllers. Let's have a look at the brake controller. Over here we can see the brake command, and in this case we have the brake command being equal for each of the 4 wheels, but as you can deduce, it would be easily changed so that you can have different brake commands for different wheels based on whatever controller you want to use. Open loop control or a bang ABS controller. Let's have a look at the ABS controller. It's a quite simple controller. Let's choose the bang ABS controller as the active controller. Let's go back inside. That's better. As you can see, you are setting the reference slip value to determine whether the ABS controller is active or not. And let's have a look at the differential control. So default is no control. As you can see, it's again quite a simple controller based on the yaw rate and steering angle. Again, let's make the rear differential controlled. Now let's have a look at the passenger vehicle model. So this would be the plant model. The passenger vehicle is basically broken down into 3 different parts. The engine as the first part, the steering, transmission, driveline and the brakes is the second part. And then as the third part you have the body, the suspension and the wheels. Let's zoom in. So the engine is an ideal mapped engine. On the driveline, we also have only the one variant active at the moment. And the body, suspension, and wheels, we have a 14 degree of freedom vehicle model selected. Let's have a look at how the mapped engine looks like. So over here we can see the vehicle dynamics block set library block for the mapped engine. It's a quite simple model we have over here. It's based on lookup tables. Now let's look at the driveline model. So in this case we have a ideal fixed gear driveline model. Over here we can see that we have the kinematic steering block from the vehicle dynamics block set library, as well as a flexible prop shaft, and the brake pressure command is also converted to an actual pressure on the brake pads. You can select between a 7 degree of freedom vehicle model or a 14 degree of freedom vehicle model. Let's have a look at the 14 degree of freedom vehicle model. Over here we have a vehicle and the wheels and tires, and of course the suspension. Let's look at some more detail inside the vehicle model, where we can choose between 6 degree of freedom or 3 degree of freedom vehicle. And over here we can see again the library block for a 6 degree of freedom vehicle model. Let's have a look at the wheels and tires. Here we can see we have some transformations from vehicle to tire reference. Then we have the tire model, and then again from the tire model to a vehicle reference. If we look into the tire, we can see we have the option of a magic formula tire or using a Fiala tire. Let's go back to the reference application. Let's now look at the visualization block. Within this complete vehicle model, over here we have steering velocity and lateral acceleration. This is the results of a previous simulation run. We also have the XY plotter, which you can modify as you see fit. And there we go. That's the complete vehicle model. The key takeaways of this part of the webinar is that the vehicle dynamics block set provides a springboard to get you started fast. These include maneuvers that can be easily customized. The Unreal Engine integration also provides intuitive results interpretation. Let's get back to our V-model diagram. We viewed the system level design. Now let's focus on subsystem design. First, let's have a look at a comparison between a car with a constant maximum brake pressure. In other words, when you just press down on the brake pedal and you don't have any active braking assistance. And let's compare that to a model predictive control anti-lock system, where we use a default slip ratio target. In each of these videos, we will be displaying both of the cars over each other, an effect called a ghosting effect. The red car is the car with an open loop, in other words, constant maximum brake pressure, and the orange car has the model predictive control anti-lock. As you can see, the red car took quite a long distance to stop, especially on the split new, in other words, with two wheels starting off on the side of the road and two wheels on the tarmac. Let's see where we added this model predictive controller. We start out with the normal reference model. We go into the controllers and then into the brake controllers. And on the brake pressure control, we simply added a third option, the MPC controller. On the standard model, you had the bang bang ABS and the open loop, we added the MPC controller. Let's have a look at the inside of that. As you can see, it's quite a simple model, and we will be focusing on optimizing the slip reference value, as you can see there. So the standard value is 0.25, and we will be changing that value and seeing how that impacts the stopping distance of the vehicle on both tarmac and with two wheels starting out on gravel and two wheels starting out on the tarmac surface. In this example, we will be looking at a subsystem of this complete vehicle model, in this case the braking controller, and we have identified the need to improve this anti-lock braking controller's effectiveness, especially when driving with two wheels off-road and two wheels on the tarmac. For this example, we will be optimizing the MPC braking controller, and the value we will be optimizing is this one highlighted by the red circle, the reference slip ratio. Here we can see the results of the stopping distance being plotted on the y-axis and the slip ratio used plotted on the x-axis. We varied the slip ratio from 0.05 up to 0.99. As we can see, there's a minima in this area right here, in between 0.1 and 0.2. The blue line is for the stopping distance on asphalt, in other words, tarmac. Let's have a look at the same situation but with split new. Two wheels on asphalt and two wheels on gravel. As we can see, there is a clear minima in this location, and this actually corresponds to a minima on the asphalt. Since we want to have equal weight for these two situations and not have the controller select according to the situation, so only one controller controlling for both of these situations, we shall be using the average of these two graphs, which is indicated by the yellow dotted line, and selecting the minima from that curve. This worked out to be 0.17. Let's view the same situation as previously, but this time between the two MPC cars. The orange car being the car with the default slip ratio, and the green car with the optimized slip ratio. As these cars are driving, keep an eye on the right-hand side to see the difference in stopping distance between the green and yellow car. It's more than one car length, and that can have a major impact in the safety of the vehicle. The key takeaways of a subsystem design is using the vehicle dynamics block set. You can test your control algorithms and easily add more detail on the subsystem where your team focuses. You can use MATLAB and Simulink together with a vehicle dynamics block set for automated optimization. You can automate for different surfaces, different tires, different driver behavior, different suspension designs, or you can optimize for whatever you want. You can also overlay the results of previous simulations to intuitively compare these results visually. Let's go back to our V model. What we did not show in the previous slide set is the fact that you can also then use this generated MPC controller and generate code directly from the model for either the plant or the controller. That means you can actually do your system testing in this virtual environment and then use the same model to generate controller code or plant code. Moving along this V diagram, we now get to the part where we start to do tests. Let's have a look at an example where we use the vehicle dynamics block set for subsystem integration and testing. We will be looking into a real-time driver in the loop simulation. In this video, we can see a driver using a real-life steering wheel controller to control a vehicle in a real-time environment and driving in a virtual scene on MCity. A bit more on MCity later on. Let's see how we used the included reference applications to create this real-time driver-in-the-loop simulation. Well, we identified the part we don't need. We don't need the predictive driver, and we don't need the scene that's controlling the driver. So we removed that, and then we added a controller. For this real-time driver-in-the-loop simulator, we had the plant model, the vehicle, executed on a real-time target machine. In this case, we used a speed goat. We had the Unreal Engine running on a computer. This also served as a visual input for the driver, who used a physical controller connected to the speed goat real-time machine. Earlier, we spoke about the virtual test environment called MCity. This is actually also not just a virtual test environment, but also a real-life test environment built in Ann Arbor, Michigan. If we look at the MCity map on the left-hand side, and we compare this to the virtual MCity map generated in the Unreal Engine, we can see that these two correspond well to each other. It's important to note that this virtual test environment is available as one of the Unreal Engine scenes included in the Vehicle Dynamics block set. One of the advantages of the Unreal Engine integration, together with the Vehicle Dynamics block set, into the MathWorks MATLAB Simulink family, is the fact that you have all the access to the post-processing power of MATLAB and Simulink. You can review your simulation results using the data inspector. You can plot signals from the vehicle model and overlay that onto a map. You can also synchronize these signals across these plots and see how different values change in respect to each other. And like I said, you can post-process the data using custom MATLAB scripts, which can automate the process of post-processing. Let's do a drive-through using this driver-in-the-loop simulation. As the Unreal Engine initializes, the vehicle is placed within the scene. You can change the camera angles using the keyboard by pressing 1 to 0 on the keyboard. There is a cockpit view also available, but for the purpose of this test, we shall use this view. Let's press the accelerator pedal and get moving. As we drive, we can see the vehicle react. This happens because the Unreal Engine is sending the ground height information to each wheel within the vehicle model. The track we are riding around in is MCity, which is a real track built in Ann Arbor, Michigan, and also available with the Vehicle Dynamics block set as one of the default scenes. As I drive around, you can get an idea of the different types of test scenarios you can author using this type of setup. You can also log signals from the controllers and the vehicle for post-processing. It is also possible to tune parameters while driving. For instance, if you were to tune the controller gains to feel how that influences the drivability of the vehicle. Over there we can see a few red barriers coming up. As the car drives through them, we can see them move. This is done on the Unreal Engine. The vehicle physics is done on the SpeedGoat real-time target machine. You are also able to do comparative runs. For instance, if you were to change the stiffness and damping values of the suspension, and you could then compare the drivability of the vehicle at different speeds in an intuitive manner by actually driving the vehicle. Using this setup, you can test the performance of your vehicle in a safe environment without having to wait for the final prototype of the vehicle, thus front-loading effort. The key takeaways of this section is that you can use a driver in the loop simulation to test scenario authoring. You can generate synthetic data for later playback or testing. You can also replace the driver input from the gamepad or steering wheel with a virtual driver to test ADAS algorithms. You can test the limits of the vehicle or the algorithms in a safe virtual environment. Let's get back to our model-based design V diagram. We did the subsystem integration and testing. Now let's have a look at system integration and testing. To do this, we will be using virtual camera data for ADAS testing. In this video, we will be using virtual camera data to do lane following and lateral control and acceleration control. In other words, we will be using the camera data to test an algorithm to identify and classify the lanes, to identify and also estimate the distance of the vehicle in front, and to adjust the speed accordingly. Let's have a look. As you can see, we are following the green vehicle. The green vehicle has braked suddenly, and our red vehicle has slowed down. As the green vehicle moves away, our vehicle accelerates until it meets its target set point of 50 kilometers an hour. Let's have a look at the lane identification and classification. On the left hand side, you can see the blue lines over here is where the lanes are identified. They are then classified as a solid line and a dashed line. Where do we find this lane following and lateral control? Reference application. Let's have a look. One of the easiest ways would be to search for monocular, and then within the results you can click on lane following control with monocular camera perception. When this opens up, you click on open model, and there you go. You can also use this demo and edit away to your heart's content. It's important to note that this demo is part of the Automated Driving System Toolbox. We've been talking about creating custom scenes as well, and to do this you will require the Unreal Editor. Included in the Vehicle Dynamics block set is the scenes that you can select from, also in a form that you can open using the Unreal Editor. Here we can see a small example of adding a stop sign to the straight road scene. Let's also do a test where we change the lighting conditions to nighttime and see if the vehicle can identify this stop sign we added to the straight road. There we go, it has identified the stop sign and brought the vehicle to a standstill. The key takeaways I'd like you to take with you as we move away from this subset is that you can generate virtual camera data using the Unreal Engine. You can refine and test algorithms for automated driving or ADAS features, and you can create your own scenes using the Unreal Editor. Let's jump back to our V diagram. We saw how we could use the Vehicle Dynamics block set all along the model-based design V diagram, from design up to testing and even code generation. We had a look into the complete vehicle model as well as the included shipping demos. Then we looked how we could optimize a subsystem of that complete vehicle model. We spoke about generating code from either the plant or the controller. We talked about using a real-time driver in the loop simulator to test some of the subsystems. And then we talked about testing control and ADAS algorithms using a virtual camera and the Vehicle Dynamics block set. Since release 2019A has just been released, I thought we could highlight some of the new features. During the presentation I showed the constant radius application, which is also new in release 2019A. Another demo that's also new is the Virtual Kinematics and Compliance Test Laboratory. You can use this to create fast but accurate suspension models by importing your test data utilizing the model-based calibration toolbox. Another new block included in the library that was quite frequently requested is a Fiala tire model. This is a simplified tire model when compared to the Magic Formula tire model and is easier to parameterize. We have also improved the body options of the vehicles. This has improved flexibility and consistency. I invite you all to download the newest version of MATLAB and to also install the Vehicle Dynamics block set. Play around with the included demos and get a feel for how it works. It really is a powerful tool